will work only with a technical problem. Okay, now, so cosmological principle. Cosmological principle also Copernican. Okay, I will not look on this. Copernican principle is very important because you will see that due to this, the equation will become more simple. And of course, as I already said in the previous lecture, so there is equation, but why universe is such a way that you see, we see it because why it's homogeneous and isotropical. So this equation we also will consider. Now I will continue the lectures about the properties of the universe, and just a second. Just a second. Okay. Yeah. And now we will consider the important point, which is related with the Hubble law and how we can receive Hubble law from using also cosmological principle and observational. I say observational point. This is expansion of universe, but in principle, if we will, usually we are using the term which tell exactly the phenomena, which represents the phenomena which we can observe. This is, I would like to say, run away. Running, it's better to say, running away. To figure it out. Okay. Away of galaxies. So the point as an observational fact that galaxy, if we will look on the galaxy run away from us, and it looks like they run away. So now we'll discuss what is it. Each galaxy, and we can also put here Hubble law. Okay. Galaxy is characterized by the spectrum, and they have an absorption line and emission line. But it was discovered that this line in the spectrum is shifted to the laboratory line. So, for example, we can know that the line is located in the spectrum and correspond to some length. But when we observe the galaxy, we can see, for example, the line of the hydrogen. It's a shift on some distance. So, we will use such a parameter, which we will call red shift, which is crucial in cosmology, in observational cosmology. What is it? So, if, for example, we will characterize with a lambda. Let's put the index obs. This is the length of wave, which we receive on the Earth from some source on some distance. And so you can write. And lambda emission. I need to check what's right. second. So, and lambda emission, this is wavelengths. I think, okay. Wavelengths, which correspond to the time when this electromagnetic wave start to emit. So I can just as a scheme I can put. So for example, here we have observer. So and here we have some object, and started. So from the object we can put here lambda emission, and here we receive this electromagnetic wave. So this is lambda observation. Okay. Due to as soon as electromagnetic wave reach the observer, the wavelengths can change, and we will use some parameter which we will call, which we put the letter Z, and we'll call redshift, which is this ratio. Right on lambda emission. So this we will call redshift, which will tell us which value and which value the wavelengths change during their way to reach observer. So, and also we can see that if, for example, if z less than 0, now we can see here, this is what observation divided under emission minus 1. So if z less than 0, it means that lambda observation divided lambda emission less than unity. So lambda observation then less than lambda emission. And it means that wavelengths became shorter due to this this way to reach us. And the shorter, it means that it's shift corresponding, for example, to the middle of the optical band. Let's consider this like a green. It shifted to the blue side, and we will tell that this object has a blue redshift. Like the blue redshift, which is correspond to the blue side. And if z more than 0, so otherwise we will have lambda observations more than lambda emission, it means that during the way, the wavelengths became larger. So, and this is we shift in the red part of the spectrum. So if we will draw it, so this is, for example, should be a laboratory line which we can investigate in laboratory, which relate to the lambda emission. So this is property of this line, and this line can shift or in this direction or in this direction. So where you put this, for example, lambda, it means that in this direction it will be red, in this direction it will be blue. It's and we will consider, it looks like a Doppler effect. We will look at this, but we will understand that this is not a Doppler effect, but it means in any case that if so in the, a little history, Because it's interesting, for example, in the beginning of previous century, nobody knows that there are other galaxies. So of course, people, and humanity only start to discover more deeply the sky, and it was even the great debate about, which is 100 years ago, what is this? What is this places? Just a second. Sometimes I lost. What is a strange nebula? Strangeness nebula. They are inside of our system, or they can be the different stellar system. So in 1921, Slipher. I'm not sure that I write right way his name, but Slipher, Vesta Slipher, he measured the redshift of the galaxy M31, and he discovered that for this galaxy, the redshift is less than 0, so it's negative, which means that this galaxy not run away from us, but go to us. And now we know this Andromeda nebula, this galaxy is a gravitating connecting with our galaxy. So this is our home group of the galaxy. Why it's like this, and why this galaxy looks like go to us. Finally, Andromeda in our galaxy, Milky Way, finally in some billion years, as give us a simulation, will meet each other, and as a result, it will be maybe one system, and of course, it will be a huge crash, but it will be not. It will be in 10 billion years, so we have enough time to live. Later, also in 1925, it was a additional measurement of galaxies, and it was already 40 galaxies. And he discovered that almost for all of these galaxies, the redshift more than 0. So only the galaxies which is around Milky Way and maybe gravitational connecting with Milky Way, they have a negative redshift, and this it means that it looks like that galaxies run away from us. So if we are here, and when I put observer, it means that we are observers. In principle, we don't know anybody else in the universe for now who else observe universe. So, in principle, we put ourselves. So, and it means that the galaxies which we observe, okay, this galaxy, okay, this looks like galaxy, but doesn't matter. So the direction like this. So they go out from us. And finally, in 1929, also Edwin Hubble, he used data of Slipher, and also he by himself observed also galaxies, and he already knows the redshift for the 50 galaxies, around 50 galaxies. And when he put on the graph the dependence of distance to the object and we will write how you can obtain the distance to the object as a function of, it's better to say, velocity of the object as a function of the distance to the object. So it also looks like this. Maybe I later will show this original graph. And he discovered that this is linear dependence, which call now the Hubble law. So this Hubble law, we will little bit later to write here. So this is Hubble, we can write now. This is Hubble law tell us that between velocity of the galaxies, object far from Milky Way, there is a linear dependence like this. So where H0 call Hubble constant, this is constant. We call it, a second. We call it Hubble constant. So it was obtained as a observational fact, and of course, as usual, and this is we call Hubble law. It was later. It was some debate about this because this law is really very important, and the debate was even a few years ago. It's continued, and because if you will look on the original picture, which was obtained by Hubble, it's very complicated to put, not complicated, the distribution of the observational points such a way that you are not sure that you can put line, so line and obtain a linear law. But it's suggested that Hubble known about theoretical work of Lemaitre. This is very famous cosmologist who was working with in a framework of theoretical point of view with the cosmology, and he predicted that if universe expand, it should be a linear dependence between velocity and distance. So unfortunately, or I don't know, nobody knows, but Hubble didn't do any reference to Lemaitre. And it's sometimes it's happened because when Lemaitre, he was a priest, and later he became the president of Vatican, so correct to say, the president of Vatican Academy of Science. So, and maybe it's called a little bit different, but the meaning is one. And when he predicted this, Lemaitre, he sent the paper about this prediction, but finally, referee said that this point is not enough clarified. And Lemaitre clean this part which tell about linear dependence, about velocity and distance to the object. But he gave a talk on the meeting, and the people believe that Hubble could hear this talk. And when he obtains this data, this galaxy, he already was preparing to put the line and to prove that between velocity and distance to the object, we can put, this is exactly linear law. So this is some story, and a few years ago, International Astronomical Union decided to recall this, why I tell this story to you, decided to recall this law as the Hubble-Lemaitre law. Hubble-Lemaitre law. So I will use, and all of us who are member of International Union voted for this, we support it or not. So I supported the idea to call this law Hubble-Lemaitre law, but I will also sometimes use just the Hubble law because we was using before like this. Okay, now we.
I'm sorry, can I ask several questions?
Yes, yes.
So how we can know wavelengths of emission, or
So,
we predict it theoretically? So no, we can observe only wavelengths as observers. So we can find lambda emission to calculate.
Yeah, look. I understand. Look, we can obtain the spectrum of the object. Okay, and spectrum consists of the different lines, lines of absorption, for example. And you can recognize that this line is correspond to the line of the hydrogen. Okay, and we know that the line of hydrogen correspond exactly from the laboratory, exactly such wavelengths. So from laboratory stuff. So we know this very well. When we look on the object, we can see, we can recognize this line, but we can see that it's shifted. So together with other lines, all lines are shifted, not only this line, but all of them shifted.
Okay, so we choose the closest line to real line, which corresponds to some chemical
yes,
substance,
exactly.
and just okay. We will consider, for example, with some objects which moves with very high velocity. Can the shift be so big that we just
Now let's
suppose
wait.
that it's other element.
Let's wait. We will reach this point a little bit later. So now we we step by step go. Now we will look. We can see that there is an observational effect, and we, of course, we will try to find the explanation of this. And this is moving of the object, or this is something else. So let's wait a little bit. So what is now? We can write. Okay, are you agree to wait a little bit?
Yes, I agree. Wait a little bit.
Okay, and you can ask questions if it will be not understandable. So it's understandable that I would like to see how much students. Okay. How many? Okay, so if we will look on the dimension of this constant, and I put here the index 0 because a little bit later, just a little bit later today, we will see that in principle this is not always constant. So h0, and the dimension, as we understand, this is kilometer per second, but okay, it's not right. I of course wrote the stupid things because 1 divided on t. So this is a value which is inverse of the time. We like to use, I mean, astronomers, astrophysicists, we like to use such a kind of, I'll call it a dimension, megaparsec. So in principle, this value if we will write in such a kind of way, kilometer per second divided to megaparsec, it can tell us immediately which velocity of the object in kilometer per second on the distance, which is located on the distance 1 megaparsec. Why it's so convenient for us. But it's understandable that final dimension is inverse of the time. And it's, by the way, if we would like to estimate the age of the universe, it's call it 0, this just 1 divided on h0. Later we'll see why, and later we'll see that this is not, so that it's only for estimation, it's not exact expression, because the age of the universe, as we will see, depend on the exact cosmological model. But if you would like to estimate, this is possibility to estimate the age of universe. So it's interesting that when Hubble obtained this value, he obtained a huge number. He obtained like 500 kilometers per second divided megaparsec. And it's funny because if you will find the age of the universe corresponding to this value, it means that the age of the universe less than the age of the Earth. And it was funny because but it could say us that something wrong. Now, this value, which is, clarified estimation of this value all time. So now this is approximately 70 kilometers per second megaparsec. But even different, because now there is another problem which I maybe will touch later. So I, for example, can use 70 kilometers per second on megaparsec. But we also because there are different kind of possibility of different possibilities to measure this value from different procedure and different observations. As a result, now we discover that this value is different. For example, 668 can be 68 or 71, and it depends on the method which you are using. And now there is discussion of this problem, but for our estimation we will use this value. Later we can discuss this one, why it can be changed like this. So 70 or 71. So okay, now I would like to discuss the first or to prove that, let's prove that if we have, and what is important also, this dependence of the velocity and dependence velocity on r, the Hubble law tell us, and please remark this in your conspect, tell us that universe expand. So this is a proof that of expansion of universe. And you can see that it's 1929, later than formulation of general relativity. So 1915, 1916, when general relativity was formulated, and Einstein wanted to apply it immediately to the model, to model the universe. And for Einstein, from the point of Einstein, for this time on Einstein, general relativity, two main papers. So general relativity. So for this time, the people believed that universe should be static, as everything which are related with more fundamental things. So, and later we will speak about the story of the lambda constant, which Einstein put in his equation to keep this idea of static universe. The universe has an expansion, so it's expand. But now we will prove that if expansion is a homogeneous and isotropical case, homogeneous case, in this case we exactly will obtain the linear dependence of velocity and on the radius, on the distance to the object. So to do this, I will do the following. Let's maybe jump to the next page. Okay, so it's really strange that the picture like this, which I put here, that everything ran away from us. We in the first to imagine it, we can imagine. Okay, I have the here place. I can put it here. So let's, for example, consider some. Okay, rubber. Let's consider, for example, rubber ball. And so it's represent two-dimensional space. So in this rubber ball, which you're using for to celebrate something, for example, for kids, we put we will draw galaxies, okay, like this. Okay. So after this imaging that this surface increase, so we put air inside and it's became bigger. So, and this ball, and as a correspondent, right, so we have, oh, sorry, that the distance between galaxy, this object, I will try to draw spirals, will increase. So this is just, you know, like how to imagine, and we are in center of this sphere. So as observer. So, and for us, we can see that this galaxy go away. And we will come back in this case. So here I will put two-dimensional. We will come back to this representation a little bit later. But now let's prove that really if we have homogeneous and isotropical case, expansion will correspond to the Hubble law, to linear dependence. This is just from mechanics. To see this, let's consider from some number of the galaxy, let's choose some three objects. 1, 2, 3. Okay, it's understandable that many others, so we choose 3. The same we can repeat with another three objects. Let's put it 1, 2, and 3. So we can put the distance here, 1, 2, here, 2, 3, and here, 1, 3. And now we consider the situation. So what means that we have a we have an extension which homogeneous and isotropical extension. What it means? It means that as a triangle, so, and we understand that in this case, okay, that's the triangle, which is which will finally to appear due to this expansion. So this is will be 1 prime, 3 prime, 2 prime. And in some, due to some time, so we can write and this triangle will be similar to the previous one. This red triangle will be similar to the blue triangle. It's understandable, yes. So if we will have this homogeneous extension. So in this case, we can write that if we will put here the distance which correspond to t0, some zero moment, and this is r12 such time t. So it means that we can write that r12 as a function of time is r12 t0, and the relation between them we can write depend only the sum scale factor. So, and this is due to the fact that the fact of homogeneity and isotropy. Of course, if it will be inhomogeneous and in non-isotropical distribution, in this case, you know, this distance can be changed much more complicated. But due to these properties, observational properties of the universe, we have just such a kind of relation. The same with, I can write for from 2, 3, for example. And it will be the same dependence, the same scale factor, A. And okay, and same 2, 3. Two times this, sorry, 1, 3. 1, 3. 1, 3. T0. Okay. So we will call A and T as a scale factor and we will decide that in principle for the future, for this our modern future, that for the present time it means that A on T0, because present time we will call T0, that scale factor we call unity. So it just means that we can do it. So it means that we consider how much changed the distance between object in future and in the past relative to the to the present distances. This is the point. So we can choose the system of coordinate which we would like, and it's enough intelligent to coincide in this case the origin of the reference system in the time with the present time. So in this case we can and by the way, all cosmology, not all, but dynamical cosmology, I say, the main goal to obtain the law for this scale factor. This is fundamental because it tells us how universe extend in the past, in the future, and it's tell us in principle from this we can understand which physical process could exist in such a kind of system. Okay, let's go step by step. So now if we would like to find the velocity, for example, okay, so let's understand the velocity. Okay, what we can see, we can dr by dt. Doesn't matter, we can put here 1, 1, 2 or 1, 3. I will omit now this this indexes. So if we look on this expression, we need to write it will be dA by dt multiply on r t0. So for example, I can write here 1, 2 like this, 1, 2. It means that the velocity of one galaxy relative to another. So, and this is a constant because, look, constant in the sense that we fixed for the present time the distance between two galaxies. So if we will obtain r from t0 from this equation, we can write that this is a point. I will call d by dt, just the point. Okay, so divide on a r 1, 2 on t. The same we can repeat for another velocity. Yes, the same procedure. So, and finally we can don't take into account these indexes and just to write finally that v, velocity of the galaxy, equal a derivation of scale factor divide on a multiply on r. So let's put it in frame. So in principle, we obtain the linear dependence between velocity and distance to the object. This, which here we have some multiplier, some factor. This factor we will call h, which in principle, as you can see, depend on time. And this is a divide, a point divide on a, derivation of a divide on depend of time. We call it Hubble parameter. So, and you understand that there is a difference between Hubble parameter and Hubble constant. So it means that a Hubble constant H0, which was H0. So this is Hubble parameter, moment of time t equal t0. So all this is a moment of time, present moment of time. So the parameter, the Hubble parameter, no, it's better to say the Hubble constant is a Hubble parameter on the present time, in the present time. Okay, so by the way, you can make as a some procedure, you know, by yourself for next lecture, for example. You can calculate T0, which is 1 divided on H0. Let's put here, if the H0 is approximately 70 kilometers per second. When we would like to use much more precise value, so we will put precise value like a 68 and refer to exactly which method it can be obtained. It was obtained, but for now, megaparsec. So if you will put this value to this formula to estimate the age of the universe, you will obtain really like 13.7 billion years. And it's really funny because, well, it's fine because later you will see that if you will take into account the cosmological model, which finally we will apply, that you need to estimate the age of the universe much more little complicated way. It will depend on which components universe consists of. So the energy, that matter, and like this. But finally, this value really will correspond the way, the simple way to estimate the age of the universe. But you will see why. So it will be really some miracle. The next one, what I would like to discuss. So what is we need to remember from this part, that the linear dependence, and I will ask you some exam and you to remember this, that linear dependence is why. Dependence is a result of the homogeneity and isotropy of the universe. Now the next step, let's consider which is the reason, which can be the reason of such a cosmological redshift. So, and how we can connect from, relate to find the relation between redshift and velocity, for example. So let's put here, and I will put exactly cosmological redshift. I put here the word cosmological because in principle we can explain this phenomena of the shift of the spectral line or some line mission to the red side with its three possibilities. And more known, of course, this is Doppler effect. So, Doppler effect. But what it means, I would like to say in advance that that when we say about redshift, which are related with a cosmological object, it's not right to explain it with a Doppler effect. Please remark it. The redshift, the phenomena of redshift of the galaxies is related with the stretching of the space. Is related with the effect of the stretching of the space. It's like a rubber ball, which we consider here, but we consider two-dimensional case. It's complicated. We can't, in principle, to imagine such a way representation, this one, in the three-dimensional case, because our brain is not preparing for this, because we are living inside of three-dimensional. But when we tell about cosmological shift, it means that the distances between galaxies increasing due to stretching of the space. It's like we have some rubber. We put here two galaxies with a fixed distance, and this distance fixed. So, but after this we are stretching in like this. So this is scale, and this became like this. Scale became huger, and it looks like the distance. Let's try put here and put here, yeah? And the distance became larger. So this is explanation, and it's understandable that as soon as we start to tell about stretching of the space, it means that we need to take into account and use general relativity, because general relativity tells us, the theory of general relativity tells us that the space can be curved, and it's curved in principle under gravity, and can be stretched. So, and a little bit later we start to work with general relativity. And this is the first point, which is about redshift. There are another point. There is a redshift which we call gravitational redshift. So, but this is a different phenomenon, and which is related with point with also general relativity, and with the effect of a deceleration of the time. So we'll look at this and consider it a little bit later. It's not so important now for cosmology. And the third, this is this effect, which you know well. This is Doppler effect. In principle, if the object has a redshift positive, but if this z much less than unity, it means that this is far object, but not incredibly far object. So not in local, so not, let's consider this is not related with our gravitating system, but on some distance, not far from us. We can use the formula of Doppler effect. And we will see now why it's more convenient to use a Doppler effect for the large scale, because the velocity of the object will be next to the speed of light from another side. From another side, and we will see later that it will depend, and we will need to involve the cosmological model. Okay, so I will remind that equal lambda observation minus lambda emission divided on lambda emission. Okay. So what is the Doppler effect? I will remind that it means that we have here the source of electromagnetic wave, let's call it lambda emission, and now, for example, we are here, okay, look on this object, not this object, we looked in this direction. In principle, this object can move with some velocity, with this vector, and this, okay, like this, and to be the source of electromagnetic wave, okay, like this. Okay, so, and in principle, and we should put here some angle, theta. So this is theta, this is angle between line of sight and the direction of the source motion. And lambda observer we put here. So, and we know this general expression for the lambda observation, which is lambda emission 1 minus, and let's consider the projection. So we will have V divided on C. C is the speed of light on cosinus theta. Okay. So it means that if we have a situation when theta less than 90 degrees, so we will have lambda observation less than lambda emission. Or if you will write for frequency, new observation will be more than new emission. So this corresponds to shift the emission on which side? Are you here?
The blue side.
Blue side, right, blue. And otherwise more 90, so it will have otherwise. And this is right side. So if we have situation, for example, which are related with the galaxy, so it means that this is direction of V. We have theta equal pi. And in this case, we, from this formula, let's put it in some frame. So this is formula of Doppler effect. But remember that this is not a Doppler. Okay, I will say a little bit also about this. So no, because I can forget. So I would like to say with the differences between Doppler effect and the stretch of the space, the difference is such a way that when we consider the Doppler effect, it means that the source moving in space relative to us, okay, from us or to us. But when we say about cosmological redshift, this is stretch of the space. So you feel the differences between the motion of the source in the space and the stretching of the space. Why is physically this phenomena are really different. So, but let's look what we have. If we will consider, if we will apply, just not consider, if we will apply the formula of the Doppler effect. So we have lambda observation. I will move this lambda emission on the left. And here we have 1 plus V divided on C. So if I will look on this one, on the definition of redshift, which equal lambda observation, lambda emission minus 1. So I can see that this, from this, that Z equal V divided on C. So I will put here that C is the speed of light, so this is approximately 3, 10 centimeter per second. Okay, speed of light. So this is we obtain the connection, the relation between the redshift and velocity of the object. So if you would like to, if you, for example, observe the galaxy with object which is not, with the Z much less than unity, you can obtain the expression for with the value of velocity V equal Z multiplied on C. And now, you know, you can feel why Z should be much less than unity, because when we speak about galaxies, the distance can be much more than unity. Okay, I mean distance redshift for galaxies which are really far away from us. And in this case, if you put here Z equal 2 or 3, the velocity will be higher than speed of light. And with this, we don't feel comfortable with such a way of things. So again, I put here that Z much less than unity. Only with this assumption, you can use this formula for estimation. For estimation, again, but again, to be precise, usually you can look on the scientific paper, and in beginning, if you even working with if you start to work with object which are far, you immediately will see the words. So we are using cosmological model, blah blah blah, and only after this you can start to discuss what you did. So also we can obtain, since we have a relation between velocity and distance to the object. So if we will put here, we have here, so we have H0 R Z multiply on C, and we have we can find the distance to the object. So it will be distance to the object. Okay, C H0 multiply on Z. So for example, we can just to feel how it's work. We have 5 minutes. We can estimate, for example, the galaxy have redshift 0.2. It's not incredibly far, but in any case, it's a object which is not in our vicinity. So we can calculate it V equal Z multiply on C, and So it's 0.23 per 10 centimeter per second. And it will be so 9 centimeter per second. So, and you can in kilometer, this is 10 in fifths. So the 4 kilometer per second. This is with such a kind of velocity, speed, the galaxy move on the distance from us, which correspond this. You can recalculate the distance, so it should be like some gigaparsec like this. So it's really an object which is far from us. So you can calculate distance as a we divide on h0. So to prove why it's now you can see why it's useful to use h0 in such a kind of dimension, kilometer per second. And now I put 70 kilometer per second divide. Sorry, I try to find the place here, megaparsec. Why it's convenient? Because you can immediately to recalculate. Let's put it 7, so it's approximately. You can see immediately that we obtain the dimension in megaparsec, and this is like okay. So this is 1 gigaparsec. So why it's useful? The dimension of h0 in kilometer per second on megaparsec. So we have additional 5 minutes, right? So because we need to finish 20, yes?
Yes.
Right? Okay. And please remind me to make a screenshot of the present. So I want to also touch the additional point just to show that universe is really, so we said about, we spoke a little about dark matter, dark energy, but we can prove now very quickly that universe is really dark, even if we will consider baronic matter. So what I mean, we can quickly recalculate if you remember the Ober's paradox. So and we used the concentration of the object, for example, stars, galaxies, multiply on L. So, and we know that this, which is dimension of this, this is L luminosity divide on L cube, L is scale, or energy divide on T, L cube. Okay. So from this survey, we know that in the local, in this some value of the universe, this value, concentration of luminosity, okay, we can call like this, is approximately 10.8 luminosity, solar luminosity. This is luminosity of sun, which we consider as a no, I think I will not be in time to finalize it. So let's continue in the next lecture, where I will show you that the universe very quickly, that universe is really empty due to the fact that we have a lot of voids, so empty places, and the galaxy distributed in knots and filaments of the huge net. But we will look on this on the next lecture. Next lecture, the first, I'm sorry, but on Friday, tomorrow I will go to Congress in Salerno, and exactly on Friday I will give my talk there. So it's Congress of Italian Physical Society, and I can't give you lecture on Friday. So I suggest to meet on Monday, next Monday. If we can to find the time, so we can move this lecture for Friday and for another day. Okay, are you agree?
Okay.
Okay, so if you have a question, please ask me now. I will make a picture. So don't go out, I make a picture of students. On the next lecture, we already will consider quickly Newtonian cosmology, it's just a short time, and formulate the importance to use general relativity for cosmology and start to work with general relativity. And after this, we will use it to solve Einstein equation for our world, for our universe. And this is the plan, near plan. Okay, if you don't have any question, so we will meet on Monday, which it will be a number, date, let me see, 18. Okay?
Okay.
Okay. Thank you very much.
Thank you.
Mhm.